Okay.
Yes. Yeah.
Oh, you can hear
John,
me. Great.
then we follow with Abraham. Is okay for you?
Yeah, that's good. I'm going to go ahead and share my screen now. If that
Great.
works. Okay. Hopefully you can see my screen, and I need to minimize that.
Yes, we
chat
can.
box. Okay. Very good. Come on, Google Slides. There we go. Okay. Okay, thanks, Peter, for inviting me to give this talk. I know it's been quite a long time coming. For those who don't know, I'm Abraham Moller. I go by John, and today I'm excited to share with you just really the beginnings and a very simple proof of concept of a ESP8266 light meter and eventually a Datalogger that relies on punyforth. It's a much more application-focused talk as opposed to the workings of Forth like John was giving. Okay, so my goal is to build a compact Internet of Things capable Datalogger that primarily would help with health and home automation, but I can think of other uses such as, citizen reporting of weather and gardening. The idea here is this Datalogger would collect in real time light, temperature, and humidity through a solar cell and a DHT combined temperature humidity sensor. I found reducing humidity has greatly improved my sleep quality, so I have a lot of interest in measuring humidity in different parts of my apartment. Certainly, DC's had a heat wave for the past several days that's just passed, and I've noticed its effect. So that's one possible use. Another is home automation. Already, air conditioners have some aspect of a homeostatic or negative feedback type of control. They have a hygrostat and a thermostat that will turn off the air conditioner once a certain temperature and humidity are reached. But at the same time, that's just right adjacent to the air conditioner where the temperature and humidity are being measured as opposed to elsewhere in the room. So there's more that could be customized with that, and definitely for lights. There's my manual feedback. It gets dark, I need to turn the light on. It's light outside, so I turn the light off. But automating that could help a lot with energy use and, again, health and so on. I failed to mention that this can be beneficial for gardening. Say you have an orchid that's really picky about light and temperature and humidity and nutrients. You might not get nutrients from this. You probably could hook up another I2C sensor or something to do that, but you could get that data in real time and tune your greenhouse or whatever garden. And I've also heard there's citizen meteorology. You can collect temperature, humidity, and light at your particular location. Anyway, so why use an ESP8266? It costs $5, super easy to power. I can hide it in a little box, and it's Wi-Fi capable. And why punyforth? Or why Forth in general? It executes very quickly. Debugging I can do interactively and a lot quicker than, say, with C or Python and so on. And of course, it has built-in words for reading from GPIO pins or the ADC, which I'll show you here, so I don't have to reinvent the wheel. So what did I use as a light meter? Well, most of you would probably think, why not use a photoresistor that will decrease in resistance given light, or photodiode, a transistor that increases gain as light is added. But instead, I chose to use a solar cell. And I'll be honest, the primary reason is I had one hidden somewhere in a junk box, but there's other benefits too. It's most responsive to solar radiation as opposed to light inside a room, which can be helpful for various applications. And there's no need for an external voltage. You just read the voltage that's induced, which you can see is proportional to luminance as well as the current output. There's normally 3 and 6 watt solar cells that I've seen And the voltage, as we'll see, is within the range that the ESP8266 can tolerate. So again, voltage here is proportional to the intensity of light. It's an incredibly difficult interface. You connect the negative wire to ground and then the positive wire to A0 on the node MCU or T out. So interfacing is pretty simple. And then as far as routines, we think in Forth in terms of factoring problems, and I think a lot in terms of domain-specific languages. One is for reading data, so having words that will read light from the solar cell, and then also for temperature and humidity. I don't have it yet, but I had a $2 DHT11 coming in the mail that I'll interface, and punyforth does have a library to handle that I'm going to study thoroughly so I understand the internal workings. There's words for printing the data in a nice tab delimited format, fetching network time. So there's a network timestamp and an up timestamp, like you'd see in Linux, as we see, with more resolution than network timestamp that goes to seconds, at least in this implementation. And network communication. The goal here is eventually to have some socket where a server could connect to the socket and then get in tab delimited format. Network time, uptime, light in terms of voltage, induced voltage, and then temperature and humidity, and then process and plot that data and start building models for different times of day and times of year and so on. So the way I'm interfacing this solar cell is through the ADC. Fortunately, there's an ADC read word that Attila implemented in punyforth, and this reads the voltage at the T out pin, which is from 0 to 1 volt. But as you noted earlier, I'm connecting the solar cell through the A0 pin, which goes through a voltage divider. And oh, someone has a question. Okay, I'll keep going. Anyway, and then the RF pin enabled. Anyway, so it reads voltage from 0 to 1 in 1 in 1024 volt increments. So I have pretty simple words right now. This example is just measuring. Actually, excuse me. Not 1 second intervals, 0.1 second intervals, measuring light in terms of voltage over a 30-second time period at a 0.1 second interval. I have two global variables that you would set for duration and interval for measuring, a word that converts this to number of iterations. I've further refined this, but a word just to get light at a certain time point. This will find the uptime in milliseconds, tab, and then read from the ADC, and then carriage return, so quite simple. And then this measure light word that will convert into iterations and then go through a do loop and add every wait an interval and then get light and repeat. And we'll notice that because I've added network time, and that has some ping time. It's not quite, say, 100 milliseconds. It might be 190 milliseconds because it has to contact time.google.com to get the time. So essentially the way you do this is set a duration, milliseconds, 30 seconds, 0.1 seconds as the interval, and then measure light for that time. So this is hello world, not in terms of programming, but just in terms of testing the hardware with your hands, literal hand waving, not making up an explanation for something that has maybe little or maybe a lot of relevance, but actually waving my hand over the solar cell, which I'll show you again after I'm done with this. I put my solar cell right on the windowsill and then started measuring for some time period, and you can see there's about 0.09 volts induced, and that was in the afternoon, so decently strong light. I put my finger on the solar cell. Suddenly you get to this trough here. I move the solar cell under the air conditioner, and there's some vicissitudes when I move it back and forth, but the amplitude of light goes down, and then I put my finger on the solar cell again. Again, this is just units of voltage. Eventually I'm going to calibrate this in terms of light intensity. Okay. I've added recently an enhancement with network time. Again, it would be useful to have a network timestamp. Again, I don't think I need to put in the overhead to process this in Forth. I could do that, in a spreadsheet or in on a server with, a higher level programming language. But anyway, it's pretty simple. There's an NTP library. I have my ESP8266 in client mode, so it's connected through DHCP to the internet. It can access network time through time.google.com, and I can print network and uptime as timestamps. So the next steps then are going to be to do experiments. Test this in different rooms and see how light differs, especially with lights off. So just I pointed towards the north, so I guess that's not super as interesting as being west or east. But anyway, so light that comes in from windows pointing to the north, different locations of the room, turning lights on and off, and seeing what intensity corresponds to me thinking I need a light on versus off. Building light profiles, again, depending on location and time of year. And the most important thing is calibrating against luminance or light intensity. And there is a meter on my phone that can measure that from the camera. Then for improving the Datalogger, again, the DHT11 will fit on the breadboard. I'll show you pretty easily, and that will add temperature and humidity at the same location. I mentioned network and uptime stamps. Making a TCP socket, I have to read more about that. So there's a data stream. And then one other thing, and I think everyone will really love this joke. There's a famous, I find funny, hopefully other people do too, joke that the S in IoT stands for security. Yeah, so you don't want to connect this to the internet and then have a free port for someone to break in. There has been a power line outage that I think was traced to a Wi-Fi coffee maker. So Wi-Fi coffee makers are bad is the lesson from there. Anyway, so this would be just on the local WAN and isolated from the internet. And with that, I'll just acknowledge Attila and Jos, who developed a floating point stack that should be really helpful. So, I could have decimal value intervals instead of limiting to milliseconds or having to put intervals in milliseconds. Peter for inviting me and his help. And I think now I can do a quick demo yeah, it looks like there's time and it'll probably be entertaining. Yeah, instead of using my standard laptop webcam, I have a webcam that can rotate here, and you can see the air conditioner and the little assembly over there. And we go ahead and stop sharing and share a different screen that's connected to the ESP right now. Oh, share. Okay, so hopefully you can see my terminal window. And
Yeah.
And I'll show you the solar cell. Oh, did someone say something? Okay. Yeah, so that's the solar cell there. Oh, here we go. Oh, it has a little bubbled window, I guess, that concentrates light. And again, just some jumper cables connecting it to the ESP8266. I'll put this back in the window and do some hand waving here. I can set 60,000 as the duration, and then 1,000 as the, oh, that's not going to work. Get rid of that. 1,000 as the interval, and we'll see. Okay, so we can see on the left the network time, the uptime, and then the light intensity. I'm going to put my hand on that, and that you can see, you can see the response in real time, coming back to normal and lower. And again, ideally, this would be on a TCP socket, and then some Java code or Python or something on a server would process this to give you a trace in real time. along with temperature and humidity. And then I'll know, 40 to 60% humidity as the experts recommend for sleep. Empirically, I can show for an N of 1. Anyway, so thanks for listening. And if you have any questions, feel free to ask.
Fantastic, Abraham.
Great. Thank you very much. Amazing.
I want to add something to this presentation of Abraham. For people who join us for first time for Forth, what is Forth? Forth is installed inside the ESP8266. So you have an interpreter. Abraham is working interactively with this Forth over Wi-Fi and Internet. And what happens? Of course, you can have today MicroPython installed in this ESP8266. But what is the problem? When I bought one of these chips 4 years or 5 ago, I had Lua installed in the chip. So I wanted to make home automation with this. And I had only 2K of free RAM to work with my program. In Lua, 2K is nothing. You can switch on and off a relay, but nothing else. You can do absolutely nothing, almost very few applications. So I went to the internet to look around and I found Forth. Oh, Forth is there. My old beloved language. So this is why I came back to Forth. And people who have MicroPython in these things will understand this problem. This is the difference from Forth to other languages. In Forth, I got over 200K free of programming space in this chip. This is very important. This is the difference, because in MicroPython, okay, you have an interpreter, but what happens with the memory?
Right.
Yeah, absolutely.
Yeah, thanks for the remark, Peter.
So, yeah, thank you for your explanation. Thank you.
Are there any questions to John?
Abraham.
John, yeah. I might not have got it. Do you have this available somewhere on the net so we can look at this, or is this still work in progress?
Oh, it's a work in progress, but once I'm all set, I'll add to my GitHub repository.
Yeah, that would be great.
Details and the diagram and everything.
Mm-hmm.
Yeah, definitely. And thanks for Peter. Thanks Peter for adding that. It's pretty simple to flash the ESP8266 and plenty of RAM free. Oh, and it also does multitasking, so you can have multiple words running at the same time.
Yeah.